much as we can. Restart again? All right, when you put weight equals 32 times 9.8 and 41 times 9.8, are you getting numbers like this? 313.6 and 401.8. Since I made up these problems, I could have a mistake. Is that confirmed?
Yep.
All right, that's Newton's.
Do you
Yeah.
have to do sig figs, or can you?
You need to do it at least at the end.
Okay.
All right, so sometimes I do it in the middle. I'm kind of like you all, whenever I feel like it. All right, I kept those. All right, so now that we have force, we can go back to sum of the torques equals ma. There are two torques created, and we need to know the signs. So this one, if this was the only guy on the seesaw, he would go that way, in that circular motion. Is that a positive or a negative torque? Once again, we see it's clockwise. But what about this guy? If he was the only guy on it, he would create this way, it's just counterclockwise. So he's a negative torque. So when you add the torques, you must include the signs. So that's why I say include the signs when we do the two torques. Go ahead and work ahead of me for a minute and add up the two torques. Again, torque is force times the radius. We're adding up two of them and setting it equal to ma. But once again, we want the seesaw to be balanced, so ma zeroes out. There's no acceleration. So that's nice. We don't have to deal with the m, because the a trumps it. You can ignore this part if you're working along. I did force and distance there. It was a negative torque, so it was negative force times distance of the first guy plus 401.8 times I don't know what, x. I don't know where he's supposed to sit. That's what I'm solving for.
You
Yes.
can move the sheet up a little to the change next.
Is that good?
Yeah.
Alright. So when we changed to mass from weight and then we stuck it in the torque formula, did you get what I got? 1.03. I guess we should sig fig that though down to 1.0. Oh, I did on the next line. 1.0 meters is where he should sit to balance the whole thing. If you got that, you can give yourself a tally. Seesaw problem will be on the test. Okay. I can hand you this transparency, Jonathan, if you need it. Sit it on a piece of white paper and you can see it. Okay? All right. Next, number 4 is a chart. And this is a definition chart. So the definitions came from that very first day on this mod. Do you remember that? So I made a chart out of it, and it looks something like this. And there were all kinds of equilibriums. So see if you can remember some of those words. And when it was still and going in a straight line, it was one kind of equilibrium. When it was still and going in a circular path, it was another kind of equilibrium.
Should we write it?
Yeah, you can fill them in.
I remember them all. It's the number ones.
That's why we're reviewing, right?
Is equilibrium going to be written on the chest? I think they're going to be like a thing on my hat.
Actually, it's not a chart at all. So I'm just using the chart to review. But on the test, they'll actually ask you a question. They'll say something like, if I throw you a ball and it's spinning in a regular, at a constant speed, what kind of equilibrium is it in? That kind of thing. So I guess the word equilibrium is there. All right, straight line is going to be translational. All the straight lines are translational. And when it's still, we called it static. That might help you get some of the other ones. If you didn't get that one, you can go ahead and try and get the other ones.
So it has to be both translational, static, equilibrium.
Yeah, you have to have all that. The translational tells me it's straight, and the static tells me it's still.
Okay.
So use that as a model for the other 3 blocks. See if you can get some points out of that. 1 tally if you got translational static equilibrium for straight still. Let's stay straight and go over here for constant velocity. It's translational again because that's straight line. But the word changes from static to dynamic. Remember that day, Annabella, a long time ago, you taught us that?
No, I didn't. That's why I wrote it wrong. I said it was kinetic.
All right, we tried to do kinetic, but it means the same thing as kinetic. All right, when we
So-
switch down to circular motion, when the object is still, like a seesaw, yeah.
So you said kinetic's the same thing. So could I write translational kinetic?
No, you can't. It means the same, but it's actually called dynamic.
What's the difference? I'm sure you've told us, but I'm asking.
They mean the same, but for some reason, this is what we call something that is going in a straight line at a constant velocity. So there is no translational kinetic equilibrium. That's not a term. All right, circular motion is rotational and still is static. And then guess what over here? Rotational, dynamic. So once you get 1 or 2, you should get the others. All right. So you can get 1 to 4 tallies from that. So tally ho. All right. Anyone need that? Jonathan, you want that? Are you okay?
I think I got it.
Okay. All right, we're on the back now. We have 2 wrenches. I don't think I drew this one with transparency. We didn't really need it. One wrench is 3 times longer than the other. So how is torque affected by the longer tool? Maybe I did write this out. Yeah, I did. This is actually a mathematical problem, but you can do it in your head. So I'm thinking, how does that affect the torque? How does a tool that's 3 times longer affect the torque? Well, I start with the equation. Again, torque equals force perpendicular times the radius. And I am going to change one of those values with a 3. So which one is going to change with the 3? Well, I made it 3 times longer, so that is r, the radius. So I went in and mathematically I made a statement like this, because I knew I was multiplying this by 3. But if I multiply this by 3, guess what? Has to go over there. Have to put a 3 in over here, and that causes the torque. Mathematical equations, principles of mathematical equations, requires me to put a 3 on the other side as well. So that answers the question for you. So the torque is 3 times more torque on the long than the short. 3 times more. And that's how you answer that. Did you get to that concept before I did? Give yourself a tally if you did. All right, then the next one,
Oh, what do you have?
pardon, 3 times more torque,
Yeah.
like that. Let's look at number 6. It's similar. This time, I'm not only changing it to 3 times longer, but I'm applying twice the force. Yeah.
Do you have to write out the math in?
No, you do not.
Okay.
But if you get it wrong, it might give you some extra points if you had some of the thinking right.
Okay.
So, you do not have to. I'm looking for the answer. All right, this next one, again, the same tool. It's 3 times longer, but I also applied twice the force. Oops, you didn't see that, did you? All right. Once again, I start with the formula. This time, I put spots everywhere because I'm going to change 2 things. So my R fell off. There. All right, so the R was tripled and the force was doubled. Do you see why I put in a 2 in front of the force and a 3 in front of the R? So that will cause me to do what? Mathematically, to keep this in balance, I have a 2 and a 3. They're held by multiplication. So what will go into that spot? It is a 6. So the answer is 6 times the torque Can you do that one in your head without the math?
Wait, what?
6 times the torque.
If you have, it's twice the force. You put twice the force over here.
Alright.
And 3 times.
Tally
3
that
times
if you were able to get that
You
before
just
I did.
multiply those together and put it over there. And it's 6 times the force. So you just multiply.
Here's the math involved if you want to look at it. Here I doubled the force and tripled the radius. So what do I do over here? 2 and a 3 causes a 6 to appear over there. So the answer was 6 times the torque for number 6. Alright, I have 2 pictures hanging, and those 2 pictures are hanging by wires that are configured differently. So they look like this. And I guess I called this one A and this one B. So the question is, which picture hanging wires experience more tension? This is not a math problem because I didn't give you any numbers. It's a concept problem. So see if you can figure out which one. I put a little clue on part B on mine. I put in the components. Pick either A or B. Which wires experience more tension? One way you might do it is you can imagine that I have a picture frame that I'm holding like this, and my hand's shaking because it's pretty heavy. You see that I'm feeling the tension? What if I held it like this? Would I feel more tension, or would I feel less tension? So, which would feel, probably just from experience in life, you can tell which ones feel more tense. The correct, you got your choice on that one? Actually, the correct answer to this one is, it is B. And do you know why that is? Let me show you why. It's kind of hard to
Got something
explain.
right.
Good. Tension on part A is right here and here. And it has to suspend this weight, obviously. And this has to suspend the same weight. The difference is, this has added another component, and it's called a horizontal component, that this one doesn't have. So these wires have to overcome the force of those horizontal components as well as the weight. So they have more tension in them to do that. That was the answer is B to that. All right. Next one, number 8. What are we looking at? On number 8.
And so is it one tally every?
Yeah, one tally for that one as well. I mean, some of them were more, like that chart thing was more. All right, what did I ask in number 8? I lost my paper. All right, on number 8, I asked to state 3 units that are possible for torque. Pardon?
We're over by 3 minutes.
Okay.
My bad.